All right, chemistry. Let's get through our second part of a video lecture for chapter 2. We'll be talking more specifically about what is in your book referred to as section 3, using scientific measurements. So what are we going to be doing here? We're going to be distinguishing between accuracy and precision in measurements. Last video we talked about measurements. Then we want to determine the number of significant figures in a measurement, apply rules for significant figures in calculations, and then write very large and very small numbers in scientific notation. So accuracy and precision. You might use these words interchangeably in common language, and that's okay. Just realize when we're in the science classroom, we're not using common language, we're using science language. And so accuracy and precision have different meanings in this context. So to reduce the impact of error, scientists repeat their measurements and calculations many, many times. Don't just do a thing once and call it good. You have to do that thing several times to make sure that the data agrees with itself. If the results are not consistent, which most certainly does happen sometimes, they will try to identify and eliminate the source of error. Measurements must involve the right equipment. Last video, I showed a picture of a set of calipers that were used to measure the length between, the thickness of a skin fold. Also showed a thermometer, which is used to measure temperature. You have to have the right equipment. Selecting the right equipment to make measurements is the first step to reducing errors in an experiment. For example, if you have the choice between a beaker, a burette, and a graduated cylinder, which one are you supposed to use? They all measure volume, but what ought you use out of those three? If an experimental procedure calls for measuring 8.6 milliliters of liquid, right, that's a fairly small amount, you would use a burette, because a burette allows you to measure a volume of liquid that is as close to 8.6 milliliters as is possible. If the procedure calls for measuring 98 milliliters of liquid, you would use that graduated cylinder because it's going to measure up to 100 milliliters very, very easily. When scientists make and report measurements, one factor they consider is called accuracy. So not only have we chosen the correct equipment at this point, now we start talking about accuracy. The accuracy of a measurement is how close the measurement is to the true or actual value. Now, if you measure something, like if you measure your height, right, you're going to get a number. Now, you have a true height, a real height, how tall you actually are. That's the true value, the actual value. The accuracy of your measurement is how close your measurement is to that actual value. It might be very, very close to the actual value. It might be very, very far from the actual value. So suppose the procedure for a chemical reaction calls for adding 36 milliliters of solution. The experiment is done twice. The first time, 35.8 milliliters is added, and the second time, 37.2 milliliters is added. The first measurement was more accurate because that 35.8 milliliters is closer to the true value of 36 milliliters. Not go too fast. Notice in this first bullet we said you have to add 36 mils. First time you added 35.8, second time you added 37.2. 35.8 is closer to 36 than is 37.2. Therefore, 35.8, the first measurement, is considered to be more accurate because it's closer to the true or actual value. Another factor that scientists consider when making measurements is precision. Precision is the exactness of a measurement. Personally, I like to use the phrase, it's the repeatability. Are you able to do that thing more than once? The example that I like to use is bowling. Everyone knows that to throw an accurate shot, you have to hit in the pocket. For a right-hander, that's in between the 1 pin and the 3 pin. For a left-hander, it's between the 1 and the 2 pin. But in order to be a good bowler, you can't just throw one accurate shot, right? That would get you one strike. you have to throw 12 strikes in order to get that perfect 300. So to be a quality bowler, it's not about being able to throw a strike every now and again. It's about how many can you throw in one game. Can you reproduce those results over and over and over? So precision is repeatability, the exactness of a measurement. It refers to how closely several measurements of the same quantity made in the same way can agree. So to go on and use another example, let's go to a dartboard.
Accuracy is the closeness of measurements to the correct or accepted value of the quantity measured. Precision is the closeness of a set of measurements of the same quantity made in the same way. Consider a game of darts. The target or accepted value is the bullseye in the center. The person who threw these darts is both precise and accurate. All the darts are grouped very close to the bullseye. This graph shows the results of an experiment that was repeated 4 times. Each time the mass and volume of the product were measured. We see that these results are both precise and accurate. They are clustered and very close to the expected value. This set of throws shows that the dart thrower is precise but not accurate. The darts are grouped very close together, but they have missed the bullseye. Here are the results of another researcher's experiments. These results are precise. The data points are clustered close together, but not accurate. Each of these darts landed reasonably close to the bullseye, but the throws are not clustered together and are not precise. In this experiment, the results would average to a value close to the expected value, so they could be considered accurate. They are not, however, precise. Here we have a set of throws that are neither clustered together nor very close to the target. This set of throws is not precise and not accurate. These experimental results, likewise, are not precise and not accurate. When looking at experimental data, precision lets us know the experiment was done carefully in a controlled environment. Accuracy suggests that the experiment has accounted for all factors that might affect the system being studied.
So obviously that video is not going to be printed in your note packet, so I've included a graphical representation of the 3 most common combinations of accuracy and precision for your reference as we move forward. Now let's talk about significant figures. First thing we need to do is understand what a significant figure is. When you make a measurement or perform calculations, which you will do a lot of in this class, the way you report a value tells about how you got it. Scientists report values using significant figures. The significant figures of a measurement or a calculation consist of all the digits known with certainty as well as one estimated or uncertain digit. The last digit or significant figure reported after a measurement is uncertain or estimated. Now that might not make sense to you, so let's show an example. So here is a good old-fashioned nail, and I'm using a meter stick to measure its length. So the quantity that I'm measuring is length. You can see on the scale here, these are centimeters, individual centimeters. So that's the scale here. So I'm going to report a certain number of centimeters, because remember, in order to accurately report a quantity, you have to have a number and a unit. The unit here would be centimeters. The quantity is length. So as we go to measure this, we can see that the nail is clearly longer than 6 centimeters. We can see that it's longer than 6.1 centimeters. We can see that it's longer than 6.2 centimeters. But now, oh my gosh, my eyeballs aren't really working very well for me to see exactly how long this nail is. So there's a little blown up picture for our ease. So we're definitely past the 6 centimeter mark, the 6.1, the 6.2. And it looks like we are past the 6.3, but not quite to the 6.4 mark. We're somewhere in between 6.3 centimeters and 6.4 centimeters. So what do I write down? Do I write down 6.3 or 6.4? Neither, right? Significant figures include all of the known digits. We know that this is past 6. We know that this is past the 0.3. So we know for sure that it's at least 6.3 something. All known digits and one estimated digit. So the estimated digit involves you eyeballing what's represented by a dotted line here and seeing that this is in between the 0.3 and the 0.4. Now, you might call this 0.5, I might call it 0.6, but I'm going to write down 6.35 centimeters. The first two digits are known with certainty. The last digit is estimated. That means that maybe I write down the 6.36. You might write down 6.35. All three digits are okay, and they are all considered significant. The reason I stopped there is because I definitely couldn't tell if that was 6.355. Right? My eyeballs are not good enough. This picture is not good enough to get any more information beyond that estimated digit. Reporting all measurements in an experiment to the correct number of significant figures is necessary to be sure that the results are true. Remember, we're trying to be accurate and approach that true or actual value. Imagine you are measuring temperature with a thermometer calibrated in 1/10 degree increments, right? 1/10. For a reading of 36.5 degrees Celsius, the three digits in the value are all significant figures. Why? Because remember, we just said that the thermometer is calibrated to 1/10 a degree, so we get the point something. In this case, it's a 0.5. This is the 1/10 spot. Right? So 36.5 degrees, that's three significant figures. The first two digits are known with certainty, and the last digit is estimated. Right? Three significant figures, two are known with certainty, the last one is estimated. So, but what if you are trying to figure out how many significant figures you should report, right? We know that there are varying numbers of significant figures. How do I know how many I have, first off? Okay. There are four rules. And different books will clump these together a little bit differently, so don't let that fool you. It's the same ideas. Some people separate these out into 5 rules. Some books even compact this into 3 rules. We're going to go with 4. Okay. First rule: all non-zero digits are always significant. 1, 2, 3, 4, 5, 6, 7, 8, 9. If they're in there, they are considered significant. They are significant figures. Zeros, however, right? That's the only non-zero. Zero is a 0 digit. Zeros get tricky, right? The other 3 rules refer to zeros. Zeros between non-zero digits are significant. So basically, if you have a 0 that is sandwiched between 2 non-zero digits, 1 through 9, that middle 0 is considered significant. Sandwiched zeros are significant. Zeros in front of non-zero digits are not significant. So if I have like a 0.32, that 0 in the front of the number is not considered significant. It's in front. It's to the left, right? It's in front. It's not considered significant. Trailing zeros, right? Number 3 talked about zeros to the left. Now we're going to talk about zeros all the way to the right, the trailing zeros at the end of the number. This is the one that really confuses people. Trailing zeros are only significant if there is a decimal present in the number. Doesn't matter where it is. Some books like to point out where it is, but the way I'm wording these rules, you don't have to worry about where the decimal is. If there is a decimal somewhere in the number, a trailing zero is going to be considered significant. Trailing zeros are not significant if there is no decimal in the number. So please become familiar with these rules. All right. So our last 2 objectives that we're going to move through: applying the rules of significant figures in calculations and writing very large and very small numbers using scientific calculation. Those aren't new. Those were on your original objectives slide at the beginning of the presentation. We're just continuing to move through them. When you use a calculator to find a result, right, which you will do, you will use calculators to do calculations here, you must pay special attention to significant figures. A calculator does not round the results to the correct number of significant figures. It just doesn't. There's no setting that you can change. It just doesn't do it. It includes as many numbers as it possibly can, and it trusts that you will report the appropriate number of significant figures. And so if you write down every single number that is in your calculator that your calculator is showing, you're going to get docked, most likely, for an incorrect number of significant figures. To determine the number of significant figures in the answer, you must first find the number of significant figures in the values used to calculate the answer. So if you're adding two numbers, if you're trying to figure out how many significant figures your answer should have, you have to look at the two numbers you added. If you're multiplying two numbers, you have to look at the significant figures of the two numbers that you're multiplying. So we have a couple of different rules that we have to go over. We have two sets of rules. One set of rules for multiplication and division, one set of rules for addition and subtraction. With multiplication and division, the answer cannot have more significant figures than the measurement with the smallest number of significant figures, right? Count how many significant figures are in every single number, every single value that you are multiplying or dividing. Whichever has the smallest number of significant figures, report your answer with that number of significant figures. But with an addition and subtraction problem, the result can be no more certain than the least certain number in the calculation. So what that means is when you're adding and subtracting numbers, whichever number goes has the fewest values past the decimal, that's how many decimal places you include in your answer. So we have rules for multiplication and division. We have rules for addition and subtraction. But if a calculation has both addition and subtraction and multiplication or division, you round after each operation. You figure out the number of significant figures after each operation. So as per normal order of operations, you would do the multiplication and division first. So once you finish all your multiplication and division functions, figure out how many significant figures you should have. Then do your addition and subtraction with those numbers. And after you do your addition and subtraction based on those numbers, then figure out how many significant figures you should have after your addition and subtraction. So you'll actually have to do it twice. There is an idea that you want to be aware of. It's called an exact value. Some values have unlimited number of significant figures. These exact values have no uncertainty, right? Unlimited number of significant figures, infinite. They're perfectly known all the way through. One type of exact value is a count value, and it's determined by counting, not by measuring. We're not using a meter stick to measure length. We're counting how many things we have. There are 30 desks in my room. There's not 30.1, there's not 29.8, there's 30 because I'm counting. You can count them. It's a count value. So that 30 isn't limited to normal significant figure rules. It has more than it would have one significant figure, 30, 3, and 0. Since there's no decimal place, that would be one significant figure. But I'm counting these. So it's considered to have unlimited number of significant figures, unlimited. So it's definitely not going to be that smallest number of significant figures that limits how many significant figures you report your answer with. Another value that can have an unlimited number of significant figures is a conversion factor. We're going to be using conversion factors a lot in this class. A lot. A conversion factor is not going to limit the number of significant figures that you report your answer with. Ignore both count values and conversion factors when determining the number of significant figures that you should report, right? Look to your problem. That's what it means. Read your problem again. Look at the numbers your problem gives you and use that to figure out how many significant figures you should report. So let's go through a sample problem here. I'll work through this one for you. A student heats 23.62 grams of a solid and observes that the temperature increases from 21.6 degrees Celsius to 36.79 degrees Celsius. Calculate the temperature increase per gram of solid. Now, I'm just going to give you a heads up. I'm going to use some thermodynamics here. You do not know this. You don't have to know this. I'm just using this simple calculation so that you can follow the number of significant figures used. You shouldn't be able to do this right now. Or should I say, you shouldn't know how to set up the calculation. What we're practicing is the significant figures, so don't get intimidated here. So first thing I'm going to do is I'm going to calculate the increase in temperature by subtracting the initial temperature from the final temperature. Now you don't have to know why, you just need to know that I'm subtracting. So I have to use a certain set of rules, right? The addition and subtraction rules. And so I have a 36.79, that's 2 decimal places, minus 21.6 degrees Celsius. That's 1 decimal place. Now my calculator is going to tell me that the answer is 15.19. But that is not what I should report, because this 21.6 only has 1 place past the decimal. Therefore my answer, which I'm going to report, can only have 1 place past the decimal. So that means I have to round to this 1's place. As per your normal 5th grade rounding rules, what does this 9 tell you to do to the 1? To round it up to 15.2. Next up, calculate the temperature increase per gram of solid by dividing the temperature increase by the mass of the solid, which the mass of the solid is 23.62. And you don't have to know why we're doing this. You just need to realize that we're about to divide. I'm going to divide my temperature increase, which is the 15.2, by how many grams, the mass, right? So I'm going to take my 15.2, which I just got from the last slide, 15.2, not the 15.19, the 15.2, and I'm going to divide by 23.62. Now my calculator is going to tell me 0.644. Now I should round this answer to 3 significant figures because the 15.2 has 3 significant figures, and it's going to limit how many significant figures my answer should have. So 3 significant figures, 1, 2, 3. This leading 0, not significant, so it doesn't count. The other thing I want to point out, notice that I have 2 units here. I have degrees Celsius divided by grams. There's no reason for them to cancel out, so they show up in the answer. 0.644 degrees Celsius per gram. Now let's move to scientific notation. Very large and very small numbers are often written in scientific notation. A number in scientific notation has 2 parts. The first part is a number that is between 1 and 10. It's not going to be 1 and it's not going to be 10. It's going to be between them. We call that number the coefficient. The second part consists of a power of 10, meaning it looks like times 10 raised to an exponent. We call that the exponent. To write the first part of the number, move the decimal to the right or to the left so that only 1 non-zero digit is to the left of the decimal. Right? That will make the number between 1 and 10. Write the second part of the value as an exponent. This part is determined by counting how many decimal places the decimal point was moved when you're moving the decimal on that coefficient. If the decimal is moved to the right, the exponent is negative. If the decimal is moved to the left, the exponent is positive. So you will have to do some calculations using numbers in scientific notation, and while it is possible for you to turn those scientific notation values into standard notation values and then do the calculation, that's going to be very cumbersome and annoying. So it's actually going to be much simpler for you in the long run if you practice doing calculations in scientific notation. Now before we move on, when you're doing calculations in scientific notation, those exponents are considered count values because you're counting how many places that decimal point moved, right? So that's not going to limit your significant figures. So let's start with that part and that point. Number 2, in addition and subtraction problems, all values must have the same exponent before they can be added or subtracted. You might remember that from, I think it's 6th grade. You have to move the decimal so that that exponent value is the same for all numbers, all values being added or subtracted. The result is the sum of the difference of the first coefficients multiplied by that same exponent of 10. In multiplication problems, the first coefficients or factors of the numbers are multiplied and the exponents of 10 are added. right? But in division problems, again, the coefficients of the numbers are all divided, but then the exponents of 10 in the denominator is subtracted from the exponent of 10 in the numerator. So let's look at a sample problem. When multiplying numbers written in scientific notation, multiply the first coefficients, right, and add the exponents. So here's my sample problem. I have 3.2 times 10 to the negative 3 multiplied by 2.1 times 10 to the fifth. So I'm going to multiply those first two numbers, right? I'm going to multiply 3.2 by 2.1, but then I'm going to add the exponents, right? First exponent plus the second exponent. In this case, it's negative 3 plus 5. Negative 3 plus 5 is 2. So the calculator tells me that the coefficient here is 6.7. 6.7. Exponent is 2. So I report 6.7 times 10 to the second power. Here's another one. Talk about division. Let's divide the numerator by the denominator, right? Divide the top by the bottom. Subtract the exponent in the denominator from the exponent in the numerator. So subtract the number on the bottom from the number on top. So if we have 6.4 times 10 to the 6 divided by 1.6 times 10 to the second, your final answer is going to be 3.8 times 10 to the fourth, but how do we get that? We're going to divide, using our calculator, we're going to divide the 6.4 by the 1.7. That gives us our 3.8. And then we're going to subtract 2, because it's on bottom, 2 from 6. 6 minus 2 is 4. So that's where we get our 4. Let's do an addition problem here. To add or subtract numbers written in scientific notation, you must express them in the same power of 10. So in this example here, we have 5.8 times 10 to the third plus 2.16 times 10 to the fourth. We can't move forward yet because one of our exponents is 3, the other exponent is 4. So what I'm going to do here, since the two numbers are not expressed in the same power of 10, one of the numbers will have to be rewritten in the same power of 10 as the other. For this example, I'm going to change this 5.8 times 10 to the third so that the exponent is times 10 to the fourth. Now you can move the decimal on the 2.16 times 10 to the fourth so that its exponent is times 10 to the third. That is just as legit. I'm just picking this one. So I'm going to rewrite the 5.8 times 10 to the third as 0.58 times 10 to the fourth. Okay, so I moved it to the left. I moved the decimal to the left once. That means I had to make the exponent larger. So what I'm actually going to stick into my calculator is 0.58 plus 2.16, which is 2.74. And I keep the same power of 10 times 10 to the fourth. All right, so what have we done in this video? We have distinguished between accuracy and precision in measurements. We've determined the number of significant figures in measurements. We've applied rules for significant figures in calculations. And we've written very large and very small numbers in scientific notation.